This video will introduce you to some of the concepts that will be key to understanding our next model, energy transfer model. Energy is a term that you probably know and use in your everyday language, but we're going to learn the physics aspect of energy. Again, remember that wonderful quote that physics sounds a lot like English. It's a foreign language that sounds a lot like English. So let's learn about our first type of energy that we'll study in physics. Our first type of energy is kinetic energy. Kinetic energy is the energy an object has when it's in motion. Kinetic energy depends on an object's mass and the magnitude of its velocity. Again, remember that word kinetic means motion in physics. When we say that it depends on an object's mass, think about whether or not you'd rather be hit by a golf ball or by a bowling ball someone threw at you. My guess is you'd probably prefer to be hit by that golf ball than the bowling ball. That's because that bowling ball has more mass, so it has more energy. Think about that golf ball again. Would you rather be hit by the golf ball that's traveling at, say, 1 meter per second, which is typically slower than someone's walking, or one that's traveling at 20 meters? That's as fast as a car would be driving. My guess is that you'd prefer that 1 meter per second golf ball, because that golf ball would have less kinetic energy. So in some ways, you can think about kinetic energy as being how painful something might be as it were to hit you. Here's our equation for kinetic energy. We'll use a capital K to signify kinetic energy, and it's equal to 1/2 times the mass of our object times the magnitude of its velocity squared. I say magnitude because it really doesn't matter if we plug in a positive or negative number since we're squaring the velocity. Some important thing to note is that all energy, regardless of its type, is measured in joules, and we use the symbol capital J for that. You can see from this equation that a joule is equal to a kilogram meter squared per second squared. Remember that in physics, the standard unit of mass is a kilogram. So when we're plugging mass into this equation, it must be in kilograms, and velocity must be in meters per second for us to get our energy in joules. Let's look at another type of energy, gravitational potential energy. This is the energy that an object has, or really a system has, due to the interaction between two masses. Typically, one of those masses is the Earth, or some other planet or large object. It depends on our object's mass, the gravitational acceleration, and where the object is located within the system relative to some reference level. Here's what I mean by that. So we know object's mass. And gravitational acceleration, that's g, or 9.8 meters per second squared, as we've used in other calculations. When I say where an object is located within the system relative to a reference level, we're typically looking at how high an object is off the ground, or off the lowest point that it can go. So if I'm dropping something above the table, and the top of the table is the lowest our object can go, typically I'm going to set the top of the table to be our reference level, or the point where the gravitational potential energy is 0. Maybe perhaps I'm dropping something above the floor, and the floor is the lowest that object can go. So then my reference level, or the point where the gravitational potential energy is 0, would be on the floor. Here's our equation for gravitational potential energy. Potential energy in general has a symbol of a capital U. And since this is gravitational potential energy, it's U sub G. It's equal to mass times gravitational acceleration, or 9.8 meters per second squared, times that height that I was discussing before. Remember, mass must be in kilograms. We know G is in meters per second squared, and height, so that it matches G, must be in meters. This, once again, will give you kilogram meters squared per second squared, or joules. Another type of potential energy is elastic potential energy. This is the energy due to the interaction between a mass and a spring. I'll point out to you that both types of potential energy we've studied talk about an interaction. They depend on an interaction, and that's true of all potential energy. Really, potential energy is energy that a system has rather than an object having. This type of potential energy depends on the spring constant and the magnitude of the displacement from equilibrium. Remember that each spring has its own unique spring constant that tells us about how stiff or how stretchy the spring is. And when I say the magnitude of the displacement from equilibrium, all that means is how far the spring is stretched or compressed from where it's at when it's at rest with your mass attached. The equation for elastic potential energy, is capital U sub S, it's our symbol for elastic potential energy, equals 1/2 kx squared, k being the spring constant in newtons per meter, and x being that displacement measured in meters. Once again, just like all other energies, elastic potential energy is measured in joules. The last type of energy that we'll discuss in this video is thermal energy. Thermal energy is the energy that's associated with heat. In this course, we'll really be focusing on the change in thermal energy. Thermal energy changes or really increases as an object moves across a surface with friction. We're not going to worry about an equation for the change in thermal energy right now. The last term I want to introduce you to is work. Now, we all have our own definitions for work. Perhaps you have a job and you call that work. Or maybe you think about homework. We say that this class is hard work. But once again, physics is a foreign language that sounds a lot like English, and therefore work has its own definition in physics. In physics, work is a transfer of energy to or from a system. Work is performed by a force. Really, I should say by an external force, or a force that comes from outside the system. Perhaps the Earth is not part of your system, but the Earth exerts a gravitational force on your system. Then that force could add energy or remove energy from your system. So anytime we're adding energy to our system or removing energy from our system, it's by a force that is doing work.